All right, let's remember some parent functions. So a family of functions is a group of functions with graphs that display one or more similar characteristics. So the parent function is the simplest function with the defining characteristics of the family. Functions in the same family are transformations of their parent functions. So we've moved things up, down, left, right, correct? We've stretched, we've compressed. The parent function has none of that, right? We all come from our parents, right? They are the OG. So our parent function is the original function. And then from there, tomorrow we'll start moving things around. Okay, but let's just figure out what our different family functions are. Okay, the first family is called a constant function. What do you notice about it? All lines are straight.
That one's kind of curved.
I forgot.
So it's flat.
Yeah.
I think that's what you're trying to say. It is a flat line. There is no slope, right? There is no rise. There is no run. So it is a line, but it is a flat line, which means it's equal to just a number. Okay. Our domain for this, what do you think it's going to be? What does domain talk about? What's it asking for?
Is it for like infinity?
Yeah, is it my x's or my y's?
Your X?
My x's, right? What x's live on this graph? All of them, right? It's not stopping. So we're going to go from negative infinity to positive infinity. So negative forever to positive forever. It is never, ever ending. There's not arrows written on here, which I know you like, but there's also not a dot. So like this would indicate it is stopping. Okay? That's not there. So it is continuing forever. All right, my range. Range is my y's, okay? Because it's a flat, there's only one y value. And what is it? It is 3. Y equals 3. The end. That's the only y value on there. So that's called a constant function because it's constantly y equals 3. There is no change happening. All right, my next one in the middle, this is linear because it's a line, okay? Now we have slope coming in. So my parent function is f of x equals x. Okay, that's without anything moving from it. The whole mx plus b, your m and your b are transformations technically. Y equals x is where that graph starts from. What is our domain for this one? All real numbers. Good. It's not stopping. Forever left, forever right. How about the range this time? How low do we go?
To like -5.
Negative infinity. How high are we going to go? Positive infinity. The graph is only showing -5 to 5. But again, if I don't have a dot like this showing it's stopping, it's not stopping. It is still moving on. Yeah. So the arrows are not written there, but they're there, if that makes sense. Okay. What's not there is a dot, and that's what matters. All right. This guy is called our quadratic family. We did lots of things with quadratics, right? That all came from when my exponent was a what in my equations? When my exponent was a 2. So this parent function is x squared. So x squared is my parent function with no transformations. There's no up, down, left, right, stretch, compress. Nothing's going on. This is the original function, x squared. Okay? There is a vertex, right? And as we move to the outside, we have a ratio, not ratio. What is it called? It's not constant rate of change because that's a line. Like a constant percent change. What do we call that? Common ratio. Yeah, maybe it was a common ratio. Okay. Notice we go up 1 over 1, up 3 over 1, up 5 over 1, right? It's not the same thing each time. It's gradually getting bigger. It's like an exponential on each side. That's what indicates it is a quadratic. It is a curve. It's a U shape. All right. What x's live on x squared? All of them. Yes. So all the way left and all the way right. Good. My ranges are my y's. What y's live on x squared? Not all of them.
Is that
How low do we go? We go as low as 0. You see that bracket right there? You see that bracket? You remember doing brackets? Brackets means it's included. So we start at 0, but we're going to go up to forever. Okay? The parenthesis we use because we can't touch forever. Okay? A bracket, though, I can touch 0. That is where my vertex actually is, when y is 0. Any questions about those top 3? They should be pretty familiar. I'm hoping this is familiar territory with you guys. Okay, good. All right, my next 3, we have cubic, square root, and an absolute value. So my next family is the cubic function. There's our graph. It is from the equation x to the power of 3. Usually when things have a power of 3, don't we say it's cubed? 2 to the power of 3, we say 2 cubed. It is a cubic function. Okay? We have a nice little curve happening in the middle. What is the domain of this function, left and right? Yeah. All the way left, all the way right. How about my range? How low do we go? Yeah, forever. How high are we going? Forever. Good. A pattern you'll see later is that if your exponent is an odd, so a 1, a 3, a 5, a 7, your domain and range will be negative to positive infinity for both of them. If you have an even, like a squared or a power of 4, power of 6, your range stops somewhere because it dips and goes back up. So pattern you'll notice later. All right, then we have some 2 special ones over here. Square root functions come from the square root of x. It looks the way it does because can you take the square root of a negative number? No. So I'm not going to ever put in a negative x value. Also, if I can't do that, can I take a square root and get a negative outcome? No, because it has to be 2 of the same thing. So we're never going to have a negative y value either. Okay, because 2 positives or 2 negatives gave me that number in the middle. All right, looking at my function. So because of that, because we can't use our negatives, what is our domain for this function? My lowest x is a 0. Good. And we're going to use a bracket. And what's the highest x we can use? Infinity. Good. What is the lowest y we can use? 0. And what's the highest y we can use? Infinity. Good. That's showing all the positives. Does that make sense? Because with square roots, we only have positives. Good. Me too. All right, absolute value. We just did some of this, right? This is the most recent thing that you've seen. So it almost looks like a quadratic right above it, but what's the difference that you notice? Like look at the graph, look at the shape. It's a V, quadratic is a U. They both have a vertex. Okay? They both have a vertex, but notice how my absolute values, we have a constant rate of change. We have 2 lines on the other side, right? My quadratic, which actually has a U in the word, right? Quadratic. That's going to be a U shape. Okay? So an absolute value, yeah, is a V because of the V in our word. So the letters do help us with these. So we have an absolute value. We have our negative x's give us a positive result. Our positive x's also give us a positive result. That's the rule of absolute value. What is the domain of our absolute value graphs? What's the lowest x we're going to use? I got all of this. What's the lowest x? Negative infinity. Yeah, forever left and forever right. Remember, domain is left and right. My range is down and then up. How low are we going to go? There we go. We go as low as 0. And how high do we go? Infinity. Good. Good. All of my y's have to be greater than or equal to 0. Those 2 things show the same thing. I do not want that camera. I don't know what that camera is, but I don't want it. We're just going to see the ceiling. All right. We have 2 more graphs. I'm just going to hide it behind there. These was the most recent thing we did. So absolute value was in our recent past. Exponentials we just finished doing, okay? Exponential growth and exponential decay. So we know growth comes from adding a rate, right? In our parent function, we have a times 1 plus r to the power of x. What is our domain here? How far left and how far right do we go? Good. We go all the way left and we go all the way right. It's beautiful. Remember, we also use that r. Same thing. Okay. My range. How low did we go? How low do my y's get? Right above 0, right? We didn't actually touch 0. We got super, super close to it, right? So this time we're not going to use that bracket. We're going to use a parenthesis. So from 0 to infinity, having that parenthesis shows we're not including 0. We're not touching it. Okay. We could also say y's greater than 0. That also shows that we're not equal to 0. Okay. They represent the same thing. I know it looks like it, but it's not there. Remember how we said it was approaching 0 in my end behavior? So it's getting there, but it's never going to actually touch it. Like our football analogy. If we're always halfway distance to the goal, they're never going to give you a touchdown. You're going to get close and close and close, but you still got to get that touchdown. All right, my other one, this one is our decay. So now we have a times 1 minus the rate. So we were losing value this time, raised to the power of x. What's our domain for this one? All real numbers again. We go all the way left and all the way right. And how about my range? How low do we go?
I'm going to say 0 to negative infinity.
Yeah, so it's just like my other one. We are approaching 0. So that means we got to use our parenthesis. So 0 to infinity. Remember, we could also say y greater than 0. So when you use the y, that's called an inequality notation. When we use our parentheses and our brackets, that's called interval notation. We're showing the beginning and the end, the intervals of the x's, the intervals of the y's. What's that?
Would the infinity sign come before 0?
No, because you always do low to high when we do it. Yeah, so it's not really what comes first in the graph. Yeah, so that does get confusing. We're not going to write down left to right. Our notation is the lowest and the highest x, and then the lowest and the highest y. Good question. All right. We good? We got our graphs? Yeah? Beautiful. What I want you to do now is I want you to do the worksheet or the page in your book. So if you're using your book, go to 249. If you don't have your book, you're using what you picked up from me. It is 10 questions where you are just going to select what the parent function is. Okay? So you got 10 bubbles. Try to do it on your own. We will discuss it together. Use your notes. Okay? I'm going to give you about 10 minutes. And then we will continue with our note packet. Okay? So work on that. Hold on. There we go. What? How do we know this was y equals x? It has a constant rate of change. Yes, look at that. Each time I move up in my x values, what are my y's doing? From negative 9 to negative 11, minus 2. To negative 13, minus 2. To negative 15, minus 2. So you're subtracting 2 each time. That is a constant rate of change. That is a slope. So that was going to be our parent function of y equals x, which was our line that had a slope. Good. Number 2, 1/2 to the power of x. Now, question. Did you look at that and know it was an exponential decay? Okay, so was the hard part picking the right function to go with it? Yes? Okay, so exponential, that means your variable is the exponent, right? So it had to be one of these two. So start with that, okay? If it's an exponential equation, your x is the exponent, okay? Now, if it's decay, we talked about our base being less than 1, right? So because 1/2 is less than 1, 1/2 is showing the decay. So we know it's decay because 1/2 is less than 1. So that's why it was that choice. All right. So this was a line. This was, oh, come on, X. It's not writing. This is, what? Then go get it. So this is exponential decay, right? My next one was x squared. It was a quadratic function. How did you know looking at the table? See how there's a middle point and then we're mirroring on both sides? This is called our vertex, right? How do we know if it was a quadratic or an absolute value? Because they both have a vertex. Was it a constant rate of change on both sides, or was it an exponential rate on both sides? So here I went down 3, but then we went down 9, down 9. See how that wasn't the same, right? -3 and then -9 this way, -3 and then -9. So that's what makes it not a constant rate of change. It's not lines. These are going to be curves, okay? So it's going to do this. Can we wait until I'm done? Okay. Number 4, you said it was from the parent function of y equals x. This is a line, right? It's in the form of mx plus b. This is a line with a slope. Number 5, we should have said it was a cubic function. It has that curve going, a little bit of a wiggle. It looks a lot like the one in our notes, but it has been reflected. So a reflection has happened with this one. All right. What?
Number 5 in the book looks different.
Number 5 in the book is a little bit different. Oh, I think there is a couple that's a little bit different. Let me see who has the book close to me. Dana, what is your book? Gotcha. 5 in the book would be an absolute value. 5 in your book, it's a table, and then there's a mirror image, and they're going by the same rate. So number 5 in the book should be absolute value if you did your workbook. Sorry about that. All right. On the back, that's not right. What should number 6 be? The second one. This is definitely a quadratic. Good. Is this the same in your book? Now I'm curious. Okay. Yes, that one should be x to the power of 2. It's a quadratic. It's just upside down, right? All right, number 7. What's happening as we move forward? So 18 to 6, that's either what? Subtract by 12 or divide by 3. From 6 to 2, that's -4. Oh, but it's also divided by 3, right? So what's happening every time? We're dividing by 3 each time. Dividing by 3 is the same thing as multiplying by what? Dividing by 3 is the same thing as multiplying by what fraction? We can multiply by 1/3. Okay, so this is an exponential decay. Exponential decay. And which one of these functions were exponential decay? We already talked about it. It was this last piece with our base that was less than 1. We're not saying this function matches this table. Okay, so that might be where we're confused. This function does not match this table. It's saying this table came from the parent function of our exponential decay model. Does that make sense? Okay, is this one different in the book? Number 7 is? Number 7? Let me see your number 7. And 8. Number 7 in the book. Let's see. -1, -7, +1. So number 7 in the book is an x cubed. Number 7 in the book should be x to the power of 3. All right, 8. From the worksheet I gave you, came from the square root parent function. Number 8 in your book. Let's see here. Number 8 in your book. Oh, it's also a square root function. See how you're in the book, your x's are perfect squares. It goes 1, 4, 9, 16, right? And then the outcome is their square roots, the y's. So in your book, that's also going to be a square root. All right, number 9. This is our exponential growth, right? So looking at it, we might have noticed, oh, I know that's exponential growth. You could label it that way. What does that parent function look like? That means that my base has to be bigger than 1. So that's why we're picking this guy. 2 is bigger than 1. That's showing our exponential growth parent function. All right, and then our last one was an absolute value because it had your absolute value bars. Okay. So did we do okay? Mostly?
You could.
Did you get at least 5? Okay, good. So at least half of them? Okay. Do you have any questions about any of the ones that you did miss? Because I did not expect you to be perfect. We're okay? Okay. Yes, we're going to start transformations. And we're going to continue this stuff tomorrow as well. All right, transformations. A change in the size or position of a figure or graph of the function is called a transformation. Rigid transformations, bless you, change only the position of the graph, leaving the size and shape unchanged. So this will be our up, down, left, right, and reflections. Okay, so it's not going to stretch or compress anything. It just takes the actual image, slides it, or flips it. Okay, what's nice about transformations, we've done them a lot because it's the same thing no matter what the function is, whether it's a quadratic, whether it's a square root, whether it's a line. If I'm adding on the end of the function, that means it's always going to move up. If we're subtracting at the end of my function, that means we are always moving down. Okay? So having a plus a on the end always moves it up. Having a minus a on the end will always move it down, no matter what kind of function we are working with. Okay? So that transformation point, so if you pick a point and you want to move it a certain way, your x is going to stay the same, right? Your x will never change. If I'm moving up, we're going to do the y value and add my a to it. Okay? If we're moving down, again, my x does not move, but my y goes down those a points. So adding something on the end moves up and down. This should be a nice little review because you know all this. We've done it before. I haven't changed it yet. It's the 20th. Okay, so vertical means up and down. Horizontal means left and right. So see how we're attached to my x now? Doesn't that make sense? Because it's the x-axis where we're moving left and right. Okay, but do you remember what's special about that? We always said inside opposite because subtracting b actually means to move to the right. Adding b makes it move to the left. Remember, if I had to solve, I'd have to add b over. Here, I'd have to subtract the b over. So that's why. Okay, over here, our y function was already on the other side. So that's why I didn't have to change my signs. If we're inside my parentheses, we have to do the opposite of it. Okay? So if I'm moving to the right, I take my original x value and we add my b's to it. My y's don't move. If we're moving to the left, we take my original x value, we subtract those b values, and my y stays the same. All right, my other two things that I could do without changing the size or shape of my graph is reflections. So if I reflect across the x, there we go. So we're looking across here. So we're gonna either flip up or we're gonna flip down. Okay, so we're gonna flip up or flip down. This is going to be shown as a negative on the outside. That makes sense because that's going to be my y's. All my y's that were positive are now negative. Or if they're all negative, now they're all positive. So that's what flips it up and down. Reflected in the, I'm not sure what's supposed to go right here. Y values? I'm going to say Y values. That makes the most sense. So your X's do not change, but your Y's are going to change their sign. So if they were positive, now they're negative. If they were negative, now they're positive. So if your Y started off as what, -2? -2 would make it a +2. Does that make sense? So that negative means opposite. Good. All right, the other kind of reflection is reflections in my y-axis. So this time, if we're reflecting across the y's, which are these, we're going to go from left to right. Okay, this is, again, it makes sense. My negative is now inside with my x. We're moving left to right. That makes sense. My x's move left and right. So we are going to reflect the x values this time. So any point on there, what's going to happen is your x is going to change its sign, but your y is going to stay the same. So it's the same y, just on the other side with the opposite x. All right. Questions about our basic transformations. Up, down, left to right, and reflections. Reflection up and down, reflection side to side. Okay. There are other transformations that distort the shape of the graph. Okay. So these are going to be stretches and compressions. They also word them as expanding and compressing. Okay, so a vertical stretch or a vertical compress, okay, we're going to multiply the entire function by something. So this c on the outside is a constant. So if there's instead of x squared, it's now 2x squared, right? Instead of just y equals x, it's y equals 5x, okay? Everything has been multiplied by a value. That is going to show a vertical stretch or compression. So expanded is the same thing as saying stretch. I know which one's happening if my value is bigger than 1 or less than 1. Okay? It says between 0 and 1 because under 0 would be negatives, and that's reflections, right? So we're not messing with the negatives here. We're only looking at that value right in front, not attaching the negatives to it. So bigger than 1, it's a stretch. Less than 1, it's going to be a compression. Okay? So what is going to change? Our y values are going to change. So x is going to stay the same. Our y values will get multiplied by whatever that c value is. So that's c times y. I'll get closer for you. There we go. So if we're compressing or stretching my y's, we multiply them by that c value. And then we do have horizontal stretch or compress. Okay, and again, everything is opposite in those parentheses, right? So if my d is bigger than 1, now it's a compression. If my d value is less than 1 but bigger than 0, now that's an expansion or a stretch. Okay, so what do we do here? My x's are going to get multiplied by the d value, but my y values are going to stay the same. All right. And you know what? I went against my own advice. Everything's opposite, right? So we're not multiplying by D. What are we doing? We're dividing by D. I'm sorry. Your x's divide by D. I'm sorry. Everything is opposite. Everything is opposite with those parentheses. See? Even we get tricked sometimes. Inside your parentheses, everything is opposite. So you will divide by the D to change your x values. All right. So we're going to do these two examples together underneath, and then this back page is going to be all you. Yup. Here we go. We got this. All right. X minus 1 squared. First off, where did this come from? What kind of function did we start off with? X to the power of 2, right? We have an exponent of 2 here. My only parent function that had that was f of x equals x squared. So that's where this one is coming from. F of x equals x squared. Okay. Now, what is different about the parent function and what I have given to me, Emma? What is different about it? Yeah, thank you, Kaylee. We are subtracting 1, and is that happening inside or outside my parentheses? Inside my parentheses, right? So if it's inside my parentheses, is that going to be up, down, or left, right? Look at what we just did. Go back to what we just did. Look, we have a minus 1. Do we agree? Use the notes you just took. It looks like this one. So we are going to move to the right. And we're going to move to the right how many times? 1. Okay, so this shows